Hi, my name is He Wang, and I'm glad to present our collaborative research between the University College London and the University of Leeds. It is called 3D Student Splatting and Scooping. It is a new alternative framework to 3D Gaussian splatting. For those who are not familiar with Gaussian splatting, it is a method to synthesize novel views from photos taken by cameras from different angles. As shown in this example, there's a stone lion statue, where the images are taken by many cameras around it. Gaussian splatting computes the image from an unseen camera, indicated by the question mark. Gaussian splatting achieves this by regressing a radiance field of the 3D space via a mixture of Gaussians. Each Gaussian has a learnable mean, covariance, color, and opacity. The learning process is to place the Gaussians at the right places with the right shapes, colors, and opacities, indicated by the morphing ellipsoids in the video. Once the Gaussians are learned, the computation of the image for unseen camera is done by a rendering process. The rendering process draws the image by shooting a ray through a pixel into the 3D space. Then the Gaussians that heavily intersect with the ray jointly decide the color and opacity of the pixel. Repeating the rendering process for each pixel gives the final image. The success of 3D GS is largely due to three key ingredients. The first is the expressivity of Gaussians. Gaussians are flexible with a learnable means and covariance, making the location and shape adaptive. Furthermore, if we see the regression of a radiance field as a data fitting problem, then a mixture of Gaussians with enough components can theoretically fit any distribution. The second is the computational convenience. During the rendering process, 3D Gaussians are projected onto the 2D image plane, aka splatting. The splatting process involves a affine transformation, a projective transformation, and integration along the ray. Gaussians have closed forms in 2 out of the 3 operations, so the forward pass is easy to compute, and it further facilitates the learning from images. The third ingredient is the optimization. Gaussian splatting optimizes millions of coupled parameters, making the optimization challenging. In addition to stochastic gradient descent, a densification process is proposed to add and allocate Gaussians to the right place. Also, a Gaussian can split, clone, and disappear as needed. Combined, these operations can find good quality local minima. Having identified the 3 key ingredients, we ask ourselves, can we improve the fundamental paradigm of Gaussian splatting? The answer is yes, and the idea is to improve every key ingredient. First, we replace Gaussian with a student's t-distribution, or simply t-distribution. Like Gaussians, a t-distribution is also parameterized by a mean and a covariance. However, what's unique about a t-distribution is that it also has a control parameter which controls the tail fatness. When it is 1, a t-distribution becomes a Cauchy distribution with a fat tail shown by the green dashed line. When it is large, it is a normal distribution shown by the blue dashed line. So a t-distribution is a strong generalization of Gaussians. It can capture whatever Gaussians can capture and beyond. A fat tail means the distribution spreads more to cover larger areas. By making the control parameter learnable, we can learn from infinite number of distribution families and therefore provides better expressivity. Next, we look at the splatting. Fitting a Gaussian mixture model to a distribution has been mainly involving using positive density components in the past decades. One example is fitting a distribution like the red curve at the top. You can use 2 positive Gaussians, one blue and one green, and add them. Alternatively, we could use 1 positive Gaussian and 1 negative Gaussian and add them. They can also fit the same distribution. In 1D, this doesn't make much difference, but the advantages of using negative components becomes clear in 3D. We show one toy example of a donut shape. We fit it with only two positive Gaussians. The learning gradient drags the two Gaussians to cover the donut shape as much as they can, but still missing the majority of the shape. We'll need at least 5 positive Gaussians to capture the hole in the middle. However, alternatively, we could use 1 positive and 1 negative Gaussian to capture the hole. Introducing negative components can potentially reduce the component number needed. Last, as the model becomes more expressive, its optimization is harder than the original 3D Gaussian splatting, especially manifested as tight coupling between learnable parameters, which causes severe issues for naive gradient descent. The original optimizer gets easily stuck at low-quality local minima. Very recently, attempts have been made to use stochastic gradient Langevin dynamics, which can knock the optimization out of the local minima by inducing noises. But we found it is still less ideal for our model. Finally, we introduce self-adaptive momentum for each parameter, so they are decoupled during learning, leading to a better local minima. Our sampling is based on Hamiltonian Monte Carlo. Also, during the sampling, instead of removing low opacity components, we also recycle them. When a component's opacity becomes low, we move them to high density areas while ensuring the overall density remains the same, so that they obtain larger gradients for more effective learning. Finally, with the 3 key ingredients replaced and enhanced, we have our model 3D Student Splatting and Scooping, or SSS. We evaluate SSS on 3 benchmark datasets with 11 scenes. When compare SSS with 7 state-of-the-art methods, due to the large number of papers in Gaussian splatting, we focus our comparison with the methods that also aim to improve the fundamental paradigm of Gaussian splatting. We use 3 widely employed metrics: PSNR, SSIM, and LPIPS. Numerically, SSS outperforms the baseline methods. Please check our paper for details. Let's see some qualitative results. First, we found SSS tends to work well in areas where there's a mixture of homogeneous and heterogeneous areas. When the heterogeneous areas are fit well, there can be artifacts in the relatively homogeneous area, such as the smudged area in the sky shown in the box, or the cracks in the clouds. On the other hand, if the homogeneous areas are fit well, there can be blurred areas, such as the blurry boundary between the sky and the trees in the far end. Comparatively, SSS captures both kinds of areas well. Second, we found SSS tends to capture the details better. Here's a scene with many objects. The metal ball is hard to capture, as it has many details such as the specular reflections and the dark dots at the bottom. In the enlarged area, one can see that SSS captures the details of the spots very well, while the other methods either miss them completely or only partially capture them. We give the comparison with the original 3D Gaussian splatting. Here is another comparison with 3D HGS, and a comparison with the GES, which all missed the dark spots at the bottom of the metal ball. With more expressivity, we expect SSS to be more parameter efficient. That is, it should need fewer components to capture similar visual quality. To verify this, we show one example where existing methods, such as the original Gaussian splatting, use at least 1 million components. We first reduced the component number to 468,000, corresponding to a 58% reduction. Some methods already start to blur the foreground. While the methods at the bottom can still capture the foreground well, we start to notice the difference in the background, shown in the enlarged area where the homogeneous sky meets the heterogeneous hill. We further reduced components by 64%, 71%, 78%, and finally to 84%. All methods deteriorate during the process, but SSS deteriorates much more slowly comparatively. To further verify the parameter efficiency, we collected statistics on all datasets. We show PSNR on MIPNERV 360. The vertical axis is the PSNR value. The horizontal axis is the number of components. Here, delta indicates the component number immediately after initialization. All methods increase the component number during learning, but we cap them up to 2.6 times of delta. Note that even 2.6 delta is still much smaller than the number of components usually employed in the state-of-the-art methods. The results demonstrate that SSS has a higher parameter efficiency in general. In this paper, we propose a new alternative framework to Gaussian splatting. It is a new mixture model with both positive and negative student t distributions, optimized by a new sampling scheme. SSS has limitations. One limitation is it slows down the rendering. Despite being still quick enough for real-time rendering, SSS learns fat-tailed distributions, leading to more components intersecting with every ray during rendering. In future, we will explore more expressive components and self-adaptive sampling processes to address these issues. Our paper and code are available on our website. Thank you.